Okay. Actually, I think it was Dion who said yesterday that something about the demo demons are with us. So it turns out that one of the things that I really wanted to show you, one of our servers are down, so I have to apologize. I won't be able to show everything that I'd like to, but I think I'll give you a flavor of the type of work we're doing, and also the importance of some of the technologies that are being developed by ChemAxon and how we can take advantage of it in the work that we're doing. I think it's quite interesting that several of the people who have been presenting today have claimed that they are not chemists and they're computer people, so they really don't understand the chemistry. In my case, I'm a chemist, and I really don't understand the computer aspects of much of this. But it's when different people from different disciplines get together, I think it's always an interesting experience. So what I've been trying to do, and actually it's not just myself, it's an entire team of folks at IBM Research, and we've been collaborating with a whole bunch of folks in the pharmaceutical industry, and that is exploring the computer curation of patents and the scientific literature. So what I'm going to do today is explain at a very high level what we do in terms of this computer curation process and give you an update on what the status is and hopefully show you a little bit of a demo of some of the applications that are being developed with the results of this work. So this is just, for those who are not aware of it, this is a picture of the IBM Almaden Research Center. It's where I currently work and where my colleagues work, and it's where we've developed most of the technology that I'm going to be talking about. So let's start with a document. And for those of you who are aware or who know me, you know that in the past I worked a lot on patent data. I was one of the folks who helped build the IBM patent server, if you remember that. It was now sold to Thomson, and it's run under the company Delphion. And in that course of doing the work on that, we became very familiar with patents and patent information. And as you know, patents contain a lot of chemical information, and they contain it in different forms. One is as text. So there are a lot of chemical names contained within the text of the document. And the other is there are a lot of images, chemical images contained within the documents. So about, I don't know, it must be almost 10 years now, 8 to 10 years ago, we started on how we could use various text analytics technology to electronically read the document, identify the chemical entities or the chemical names, and then convert them into structures. And we've been working on this, well, as I say, for many years, and it's a long journey, and we're still in the halfway through. But the idea was to take these documents and to do an analysis of the text. And more recently, we've started doing what we call image analytics and the analysis of the images on a large scale. And then there's also the manual curation processes that take place. And what we've been trying to do is integrate these three streams into a large database. Once we have this database, we can then combine it with both internal data or with metadata, and then make it available through a number of different applications. So very briefly, here's an example of a text of a document. And the challenge here is, what is that compound? And even those of you who are knowledgeable of chemical nomenclature find it quite challenging to convert that rapidly into a structure. So what we've been working on is developing computer methods which allow us to very rapidly take this and convert it into a structure. So once that's done, well, the process of doing that, actually, I should say, ChemAxon has some very nice tools, including a new name-to-structure program, which will enable this transformation of chemical names very rapidly into chemical structures. The challenge, of course, is once you do one set of data for example, you do US patents, the next thing people want are European patents or WIPO documents and so on and so forth. So those other documents, a lot of them require OCR because they're only available in image-based systems. And once you OCR these documents, one ends up having a plethora of OCR errors and other errors which make the conversion of the chemical name into a structure often leads to very challenging, it's very challenging in order to do that correctly. So one of the things that we're really most anxious to try is this structure checker, because as a result of this, we end up getting some significant errors, as you can imagine. And so that's one of the other applications that we're very interested in looking at. In terms of image analysis, we did some pioneering work, I'd say over 10 years ago, maybe 12, 15 years ago, on image recognition. And what we started doing more recently is trying to scale the image analysis up. And so here's one of the original papers, which if you're interested in, I'll be happy to provide anyone with a copy of. But basically what this does is it takes the images from the documents, you scan them, separate them, vectorize them, segment them, clean them up. You OCR the characters within the image, and you aggregate this and ultimately end up with a smile string. So since we did this initial work, there have been a number of programs that enable us to scale this, and other commercially available programs that can now do this operation. The problem is, once again, you get a lot of dirty structures and a lot of, well, let's just say inaccurate structures. A lot of it's just rubbish, actually. But on the other hand, you also get an awful lot of good compounds. And this, again, is where we can use a lot of the ChemAxon technology to help us post-process and to clean up all of these literally millions of structures which we've been working on aggregating and processing these structures into a database. So again, one of the problems with doing this is what one ends up with is, in fact, a smile string or a MOL file. And here again is another opportunity for the ChemAxon tools for doing not only the name to structure, but also now to assign a name to these and to do what we call the structure to name conversion. And again, another huge opportunity for the structure checker. So here's some examples. This was provided by Dr. John Kenny at DuPont. And the work, I should say, for the optical recognition of the images was done by Igor Flipov from NIH, and we've been using his OSRA code, which has been modified by John, in order to create these and to scale this up on a fairly significant large scale. So here's the original image on the left. It goes through that process that I just showed on the previous slide, ends up with a smile string, and then here's the structures that are generated from those smile strings. And here's some more examples that gives you an idea of the complexity of molecules that can be addressed. And we're currently trying to scale this up so that we can run all the WO filings, and we're actually starting to run some Chinese documents through here and extract the various compounds from all the different patent issuing authorities. So what I've shown here, and I'm getting to the chemical search in a minute, but is how we take documents and we process through basically 3 different streams. We do the text, the name to structure into smiles. We do the images into SDF files. And then, of course, we have the problem of normalizing all these. And here we have MOL files and CDX files. And again, this is another opportunity for these chemical informatics tools to help us organize this and to build a rather large database. To give you an idea on the scale, we've actually benchmarked our some of these curation processes, particularly the one over here on the text side. We've optimized it on an IBM Blue Gene, and we've actually benchmarked it at doing 1 billion pages in 3 hours. So it's a fairly high-end method of identifying and building very large databases very quickly. So being an IBM shop, we use DB2, and there weren't really any chemical cartridges for DB2. So we contacted some of the folks at ChemAxon, and they were actually very helpful in helping us devise a system. So I have to confess, I'm talking about this is work from some other folks. These are the computer folks who actually made this happen. But as I was told, we run a DB2 version 9.5 Enterprise Edition. It's on a X Series 366 Xeon processor, 16 gig of RAM on something called CentOS. And from that, we export millions of molecules. In this case, we did over 7 million molecules. And what we end up with is a SMILE string plus a chemical name. That was pulled into this red bracket, which is what I call where this code happens. It's the API, which enables you to convert the SMILEs into inchies and then into inchy keys. And then they use the JChem manager to build what we call the ChemAxon All Molecules table. This table contains the mole ID, the ChemAxon SMILEs, the formula, molecular weight, and other data, including something called the fingerprint and the JMoL Zip file. I'm not exactly sure how all this works, but from what I understand, it's this fingerprint and the JMoL Zip file which enables one to do these queries, but we can then put in a query here. It goes through a Java API in JChem and basically does the searching, which you've all seen earlier today, and enables us to provide a hit list. We filter this result. We take the top 100 molecule IDs. They're transformed back into SMILEs, and then it goes into the database where all the data is linked between the patent corpus and the Medline corpus. And the end result to a chemist is that you have the ability to simply draw a molecule, click a button, and then search and find the occurrence of that molecule in either the patents or the Medline literature. And to us chemists, that's pretty magical. That's really significant. And so we've scaled all this, and we currently have annotated, and we continue to annotate and re-annotate every page of all the US documents, the European patents, as well as the WIPO, the PCT documents. And we're just now starting on foreign filings such as the Chinese and Japanese corpus. So the bulk of what we do is not really the chemical informatics so much is the curation and the obtaining of the raw molecular content from the documents, but then we're very dependent on having these tools available to us to do the post-processing and the cleaning up of the results of this text and image analytics. So I just was asked, I'd like to summarize some of the different ChemAxon technologies that can be used in this overall process. Basically, the name to struct, the structure to name, the structure checker. Marvin View we use as to view the results. We also use Marvin to draw the input and create the input for this. And we're currently, I guess we've annotated over 18 million Medline articles, general notes. We annotate over 100,000 documents a month, and we have a rather significant database that we're currently building. And what I'd like to do, by the way, this work, I want to say it's not just my work, it's the work of a whole team of people, including a significant number of pharmaceutical collaborators. So with that, I would like to show you a little bit of a demonstration. We've developed an application called Simple. This is the actual Simple application here. I can start with the basic search menu. And this is the application that I apologize with. Apparently one of our servers is down, and the one that I need to do the most the chemical search on, but I can show you some of the details of how this works. We have this Simple application, and all the data in here was derived from the various processes that I just described. But if you click on the Chemicals tab, for example, you have the ability to draw a molecule and using Marvin here, and you can execute a chemical search. Here, for example, we get back a molecule that I drew. It had a similarity ranking of 1, which means that it was an exact hit. Here are the 24 synonyms for that molecule. So these are the all the different chemical names that our program picked up, and every one of those names converted into the same structure, which was this structure. So in theory, to do this by text searching, you would have to have typed all those different names to find all these different hits. As you can see, this column is empty because one of our, as I said, there's something down back at Almaden, but it normally would show the number of patents that contain this molecule, and this shows the number of Medline articles that contains that particular molecule. And then if you click on this, it takes you to the actual documents, which would show in here. And I apologize that link is apparently off as well. But in addition to doing the chemical search, and by the way, if you want to come back tomorrow or sometime when this is up, I'll be happy to show you this real time. We have an annotation window where you can come in here and you can actually cut and paste a whole bunch of chemical words. So for example, if I were to come over here and let's say let's see, I should have a folder here with some demo yeah, here it is. Well, here's some words here. If I just take a whole bunch of these chemical words and I can do a Control-C, come over here, do Control-V, and hit annotate, this will actually run off, and you can convert all those chemical names into structures, and it brings it back and shows the actual structures real time to show you how the process actually works. In addition to having that annotator, by the way, you can annotate not only for chemicals, but CAS numbers, FDA drug names, biomarkers, genes. We have a whole family of different annotators that we're developing. If I click over here, we can do reports. For example, let's say you wanted to find out who was patenting what. I can click over here, and what this report does is we compute this every night, and it shows all the new compounds that have been patented in the last 90 days. So, and in order to make this report, the compound has to be novel, has to be in claims, and has to be within the last 90 days. So here I can see that these are the people who are patenting the most compounds. If I scroll down, let's say I want to see what Pfizer's patenting. They had, in the last 90 days, 69 new molecules contained in 4 different patents. If I wanted to see what those molecules are, you click on that button there, and we can actually scroll down, and it shows us the document number, and these are all the molecules that were patented by them in this document. And scrolling down further, we can see all the molecules that were patented in this WO document and in this other WO document and so forth. So you can see there's a little error there that has to be fixed up. It's not a perfect system, but it's a pretty cool tool that a lot of our colleagues have found very useful. If I actually want to see the document, you can click on the actual document, and what you see here is, I'll try to make this bigger. Here you can see all the content. There's a little error code there. That's probably what's broken here. But if I click on the full description, you can scroll down, and these are all the molecules that were curated out of the document. So as I scroll down here, you can see, for instance, all of these molecules are in the database as a clean molecule. All the reactions are shown there as well. And the data's all been hyperlinked to multiple databases. So the chemical content for this particular document is shown at the bottom here. And under normal conditions, you'd be able to hyperlink to a number of different databases for if that molecule has occurred in those other databases, such as the ChemAxon database being developed at EBI. And we have hyperlinks to that as well as NCI and some others. So I think, I'm sorry I couldn't show you the actual, some of the actual chemical searching, but if later today or tomorrow you'd like to contact me, I'll be happy to give you a search of the chemicals, structure, substructure searching capabilities. So thank you.
Questions?
Are there any questions?
I do. I've got Pat back here first, and I'll get you right.
Steve, just curious, when you did that billion pages on Blue Gene, do you know how many structures you got out of that, and then how many of those structures were reasonable and didn't violate valence errors?
Well, I don't know how many we got out of a single run. What happens is, the way this works is typically you do a run, and then you find a whole bunch of things that didn't work because they have broken brackets or spaces or things like that, and you make a correction. And then when you make a correction, you get a whole lot of new compounds, but then you have a whole lot of compounds that now become unrecognizable by the various programs. So you have to actually do multiple runs, and then we aggregate the data. In terms of the quality, I would say right now what we're doing is, and it's controversial, we're keeping everything we get, including all of the, shall we say, the grotty compounds, where they have bad valences and sometimes 5 bonds to carbon and things like that. These type of inaccuracies often show up. We currently keep all of that, but what we're doing is we're post-processing the data, and we're actually starting to tag the data, because there are some people, for instance, who want to get rid of a lot of that noise. They don't want to have reagents. They don't want to have chemicals that are commonly occurring. But yet there are other customers or clients who may sell solvents, and they want to know what solvents are being used. And so there's a whole spectrum of people who want to use this. So what we're currently trying to do is to tag all the molecules as a verified whole molecule, a Marcouche scaffold, a fragment, and so forth. And we're starting to put filters on this. But to answer your question, we get a fair amount of inaccuracies, but it's still valuable, I believe, once it's cleaned up. And if you'd like to see it for yourself, I'll be happy to provide you with access to the database, and you can go into a specific document, and you can look at the raw data that's been obtained from that particular document. So you can actually do your own evaluation.
Giedeweg from Roche. I'm wondering if you have a new patent, just published patent. How long does it take until you have fully analyzed that patent? Days, weeks?
We usually get the patent data within 6 to 8 hours of issuance. So we buy a direct feed, which we get from the patent office. The European data takes longer, but usually it's within 24 hours or so. Once the patent comes into our site, we annotate it immediately, and then it gets added into our database. And then the database gets replicated every night between 12 o'clock and midnight out to the various collaborators. Pardon me?
Fully curated?
Yeah, well, yes. The data that was extracted in the MOL files, they get replicated out, yes, as well as the text. I should say that I should limit that to currently to the text stream. The image stream is still, we're still developing the image analysis stream. But as far as the text stream, that gets replicated every night.
But then if you have images, we have patents, many patents which just have a table with images. How long does it take until you have that done?
It depends on the patent issuing authority. For the US data, it's within hours. So
yeah, there you have the MOL files behind, I know.
Yes, we have
the other ones. That's the interesting part.
For the US data, we have what's called the complex chemical work units, as well as the sequence data, and that gets replicated out every night. For the WO and the EP documents, it takes, I would say, a week or so before they enter into our system.
This may be a naive question, but I wonder if all existing technology, is there an effort to make this whole process easier, like making patent office accept some kind of documents which are computer readable, like XML files or something like this?
That would be a dream, to get rid of Marcouche structures. It's a complicated world, and it's getting more complicated. I gave a talk to one pharmaceutical company, and when I actually showed them a demo and we brought up a patent and I pulled the chemical structures and you can mouse over and see the structures, and he saw what we were doing with the text analytics, he vowed that they would never file another patent with a chemical name in it, but they would all have structures, pictures, and compound 1, compound 2, and so forth. And now we're obviously doing image analytics, so we're taking out all the image data. I've started to see patents appear with inches in them. Some of the extent to which people go to obfuscate the data is pretty amazing, including such tricks as underlining all the chemical words now to try to throw off the annotators. I mean, there's a whole bunch of things. Unfortunately, it's getting more and more complicated for the patent offices. The examiners often can have a hard time understanding what's being patented. The scientists that I've encountered in the field have a very hard time understanding what's being patented. And my fear is that some of these patents get issued and they say, well, let them argue it out in the courts, and it gives rise to costly litigation. But the chemical obfuscation is a problem, at least from a scientific perspective. I'm sure there are legal people who say, well, it's protection. Yeah.
So Steve, I'm going to ask for the moon and the sun here. Are you guys working on any parsers to associate metadata with the molecules? So for instance, word occurrences might suggest that an IC50 is associated with this nearest molecule. Can you do that yet? Because I hate going through tables and flecking out IC50s.
Yeah, what you're mentioning has come up, and it's in the queue. I could say that this is a journey that we started years ago. We started with just simply doing chemical words. Now we're doing chemical images. We're doing gene symbols and so forth. What you're referring to is what I call contextual analysis. Is something an agonist or an antagonist. There are some other third-party softwares that do address that problem, and we're looking into, having some discussions. There's a company called Linguamatics that has a program called I2E. There's TIMAS. There's a number of people who focus specifically on that kind of what I call contextual analysis. And so our challenge is, do we simply partner with somebody and run those applications over the data, or do we try to develop it ourselves? It's always a buy versus build decision. So,
piggybacking, oops.
Sorry.
Piggybacking on that question, assuming I'm working on some key projects internally and I've extracted some information, can I write that back to your system so that I can annotate it for my internal users?
Actually, you can. You should. You have a copy of the database over in Mundell, and I can give you the names of the folks in Sweden who are managing that. And actually, we're just updating their database right now with about 12 million new structures, all of which have been tagged, whether they're whole molecules, fragments, or what have you. But in theory, you should be able to do that quite readily.